Alrighty, so somehow I managed to delete the last recording, so Zoe didn't hear all that stuff. So we're starting uniform circular motion. Here's the intro quiz that goes with it. So here we go. You are spinning a bucket attached to a string in a circle above your head. You probably did that as a kid, maybe, with water in it. You know, you spin it around like this, water in it. A something force holds the stopper in a circular path. Correct answer is A, centripetal. Centripetal is the correct answer. Centripetal. Sure. In a washing machine, now some of you may not be familiar with this washing machine, right? You may just think that clean clothes just naturally appear, perhaps in your room, but does she? Good for you, Mike.
I don't do anything.
In a washing machine during the spin cycle, the force is on the water, the clothes, or I don't know, causing the water to be separated from the clothes. The force is on the
clothes.
The clothes.
If I put C, would that be wrong?
Well,
Can't mark that wrong.
Can't. The force is on the clothes.
Well, I only got one wrong.
A tube has been placed upon the table and shaped into a 3/4 circle. A golf ball is pushed into the tube at one end at high speed. The ball rolls through the tube and exits at the opposite end. Describe the path of the golf ball as it exits the tube. Does it go up A, back up where it began? Does it go sort of in between at C? Or does it go straight along the table at B? And my friends, the correct answer is B.
Oh, I put A because I wanted it to be that one.
Yeah? It would be.
If you're gonna hide the speed, I was hoping it'd be. Never?
Comes right out the bottom.
Not even hide the speed.
No.
I just could have thought of like golf ball thing with the tire.
Yeah, that's right. Mini golf, right? Absolutely. Good point. Does it matter whether it started there or whether it started, like as you said, in the mini golf, or it started down here? Like, does the mini golf thing work just because it starts down here? You started up there somehow. Like, you're not going to putt it like that, but it would still be B. Still be B. Mr. Bennett is spinning a rubber stopper at a constant rate of 3 revolutions per second. The rubber stopper is accelerating.
Yeah, sure.
Constant 3 revolutions per second. Excellent, Zach. Zach said the direction is changing, therefore we are accelerating. Correct answer is true. Accelerating. Direction is changing. Now, it's still spinning. If there is an acceleration, Zach, there must be a force. Newton says that forces cause accelerations, right? So if there is an acceleration, there must be a force. What direction is the force? Is it in, is it out, or tangent? Correct answer is A. It is in. The direction of the force is directed in towards the center.
Out and tangent are pretty much the same.
Well, out I would mean like, like straight out, right? Like I was thinking, if I were to draw it here, I was thinking like in, out, tangent. Right? If it's going that way, right? Counterclockwise. So it's actually in. Okay? Because guess what? Can you push something on a string? Like if I put this on the table and attempt to push.
Well, this is like compression. You can't compress a string.
It doesn't work. You can't push on a string. You can only pull.
So you're pushing most of the other way.
What do you mean the other way?
Push the ball.
Yeah, push the stopper.
Oh, okay. But
it's pulling the string.
But when I spin it in a circle, am I touching the stopper? I'm only touching the string. So I can only pull. The force is in.
But isn't there an equal opposite reaction force?
So you get burned.
Well, see, things get a little tricky here. But we'll get on to that. We'll get there. We'll get there. When you're driving your car, now this is kind of a weird feeling. When you go out at lunchtime, let me just make this a little bit smaller here. When you go out at lunchtime here, I'd like you to think about this if you make a turn. When you're driving your car and you make a left turn, friction between your tires and the road causes the car to move to the left. You're making a left turn. The car is going like this. Is it true or false that the tires cause the car to move left? There's friction between your tires and the road that actually pushes the car left. In other words, the force on your car is this way.
Yes.
And the correct answer is that's true.
Like when you're going around.
When you turn the wheel, right, and you think about this as you're driving, don't think about it too hard because you might run into something. But as you turn the wheel, it's actually your car's trying to do what? It's trying to go straight, and it's friction that's actually pushing you sideways. Which would be why, if it's icy, when you turn the wheel, what happens? You don't turn. You're running with a snowman because there's no friction. Low friction, exactly. All right, we did fairly well there. All right, so you might recognize some of the graphics from this handout from that quiz because that's where I got it from. So it says here, if you whirl a tin can on the end of a string, just zoom in a little bit. If you whirl a tin can on the end of a string, Stefan, you find that you must keep pulling on the string, and there's a picture of that right here, 13.4. You pull, guys, you pull inward on the string to keep the can revolving over your head in a circular path. A force of some kind is required for any kind of circular motion. Any force that causes an object to follow a circular path is called a centripetal force. Let's just highlight that. Any force that causes an object to follow a circular path is called a centripetal force. And centripetal means center seeking or toward the center. The force that holds the occupant safely in a rotating carnival ride, and I don't have a picture of that, but they have the one that comes every year, right?
G-force.
G-force, is that what it's called?
And you spin up the top and get out.
Well,
Strawberries.
yeah, that one, but the G-force is a better example because you go in and you stand in your little cubicle thingy, right? And you ever notice they put that little, like, chain?
It's not even like
It's
just a chain.
Yeah, it's like you might use that kind of chain to keep your wallet in your pants kind of thing. That's how heavy duty it is. Is that chain doing anything?
No.
No, it's simply there to make people think they're safe. It has nothing to do with the chain. When you are rotating like this, and then it goes up sort of on edge, right? And you're actually spinning like almost at 90 degrees, right?
Yeah.
What's keeping you in place?
Centripetal force. The chain. Force.
No, not the chain. In fact, if it all of a sudden stopped,
You drop.
would you?
You probably snap the chain.
Well, you'd hit the side first, and then you.
Yeah, you'd hit the side and you try to keep going sideways, right? And then you'd bounce, and then you'd maybe fall, and then the chain would be. Is it going to stop you, that chain? No, you got no chance. It stops, okay? It's basically inertia that's keeping you in there. Okay, so the force that holds the occupant safely in a rotating carnival ride is the center direction force. Without it, the motion of the occupants would be along a straight line. They would not revolve. Now, centripetal force is not a new kind of force. It is simply the name given to any force that is directed at right angles to the path of moving an object and tends to produce circular motion. So it's not a new kind of force. It could be gravitational force. It could be electrical. It could be friction. It's just a force that makes something going in a circle. Any kind of force. Even the force, if you will. Gravitational and electrical forces act across empty space. So centripetal force is gravitational force directed toward the center of the Earth, holds the moon in an almost circular orbit about the Earth. Electrons that revolve around the nucleus of an atom are held by an electric force that is directed toward the central nucleus. So those are all examples of centripetal force. Centripetal force plays the main role in the operation of a centrifuge. Anybody know what a centrifuge is?
It was out.
It separates.
And over at the hospital, what's it used for? Do you know? The centrifuge? Anybody know? Yeah, it does have to do with blood. What does it do, Zach? You know?
Filter.
Separates blood from.
It does. It separates the blood. Separates the plasma from the blood. Exactly. Put it into a centrifuge. It's basically. Anybody use a salad spinner at home? You know, you wash your lettuce. And yeah, that's a centrifuge. Okay. Same thing with your washing machine. A familiar example is the spinning tub in an automatic washing machine. In its spin cycle, the tub rotates at high speed. The tub's inner wall exerts a centripetal force on the wet clothes, which are forced into a circular path. The tub exerts great force on the clothes, but the holes in the tub prevent the tub from exerting the same force on the water in the clothes. If there wasn't holes there, what would happen? The water would just stay in there, right? Exactly. The water therefore escapes. It's important to note that a force acts on the clothes, not the water. No force causes the water to fly out. no force causes the water to fly out. The water will do that anyway, as it tends to move by inertia in a straight line path, which is Newton's first law, unless acted on by a centrifugal force. So interestingly enough, the clothes are forced away from the water, not the other way around. So it's the absence of a force that allows the water to move away from the clothes. Because you can't hold the water in there because of the hole. That's the way it's set up, right? So when an automobile rounds a corner, the sideways friction between the tires and the road provides a centrifugal force that holds the car in a curved path. If the force of friction is not great enough, the car fails to make the curve, and the tires slid sideways, and it skids. We know that. We know that, right? Being winter drivers here. Alrighty. So what is this centrifugal force that everyone always talks about? In the preceding example, circular motion was described as caused by a center-directed force. Sometimes an outward force is attributed to circular motion. This outward force is called centrifugal force. Outward, centrifugal. Whoa, what's going on? Outward force is called centrifugal. Centrifugal means center fleeing or away from the center. In the case of the whirling can, it's a common misconception to state that a centrifugal force pulls outward on the can or the rubber stopper. So when I'm spinning it around a circle, is there a centrifugal force on the rubber stopper? No. There's a centrifugal force on the string. I'm pulling on the string. The string in turn pulls on the stopper. Now, because of Newton, right? Equal and opposite. If the string pulls on the stopper, guess what? Stopper pulls on the string. Is there an outward force on the string?
Yeah.
Yes. That's the centrifugal force. Is the outward force on the string. Inward on the stopper, outward on the string. Okay? That's the centrifugal force. If the string holding the whirling can breaks, it's commonly stated that a centrifugal force pulls the can from its circular path. But the fact is that when the string breaks, the can goes off on a tangent straight line path because no force acts on it. What did Newton say? An object in motion stays in motion. So I'm going to spin the rubber stopper over my head, and I'm going to let go at the exact moment to hit Zach in the head. Where would that be?
Now.
When it's like at the front?
No.
Not there. Not there.
Yeah.
There, right? Right there. Because at that instant, what's its instantaneous velocity?
This way.
Right at Zach's head.
Got it.
I'm going to. Well, put safety glasses on first.
So those people are saying,
Mary, watch out, because sometimes I've been known to miss.
Go.
you're a cowboy.
Oh, I missed.
We don't take either. Try again. Better luck next time.
Better luck next time.
Go.
But now, is it because of a force that it went, did that fly out?
That's because they
Absence of a force. Absence of a force, inertia. Suppose you're in a passenger in a car that suddenly stops short. Someone slams on the brakes. You pitch forward against the dashboard. Bang! When this happens, you don't say that something forced you forward, right? Nothing pushed you forward. You know that you pitched forward because of the absence of a force, which a seatbelt would have provided. Similarly, if you were in a car that rounds a sharp corner to the left, you tend to pitch outward to the right, not because of some outward or centrifugal force, but because there's no centrifugal force holding you in a circular motion as the seatbelt provides. The idea that a centrifugal force bangs you against the car door is a misconception. So if you imagine we're all in a big bus and I'm driving up here, and I crank the wheel to the left, what do you guys do?
It's a sign.
You want to go to the right. Now, do you actually go to the right?
No, you spin.
You just keep going straight, but the bus is going left. You feel like you're going right, but you're really just going forward.
Inertia.
Inertia.
We tried doing the thing on the bus where you toss the ball and it's backwards.
Yeah.
It doesn't work unless the windows are all down.
Have you ever, what would happen if you had like a balloon and we were in a big bus, you had a balloon and I cranked the wheel left?
It goes
Would the
right.
balloon go with you guys?
Yeah. No, it doesn't.
Would it go left?
No. Because it's in, the windows are rolled down and go
No, the windows are rolled up.
right.
If you're an orange, you'll have the window.
What about a helium balloon?
They'll stick to the roof.
If I crank the wheel left, which way would the helium balloon go? Still to the right, you think?
No, it's not a forward motion. It has no mass. It might not go as much.
Just see if you can find me a video with the helium balloon.
It might not go as much, but it still has mass. So
I'll show you right away. So when you swing a tin can in a circular path, there is no force pulling the can outward. No force pulling the can outward. Only the pull by the string acts on the can and pulls the can inward. The outward force is on the string. The outward force is on the string. Now, my friends, if we have a force, we have to have something to produce the force, right? Like a gravitational force or electric force. What produces the force on the string? I'm producing the force on the string, like on the pulling it in. What produces the force outward? Gravity from the Brome stopper?
Is there a force over us in the sun?
Yeah, it's back.
Kind of confusing.
Yeah.
That's not a normal force. Now, suppose now we're not talking about rubber stoppers. Suppose we're talking about cans. Suppose there's a ladybug inside the can. The can presses against the bug's feet and provides the centripetal force that holds it in a circular path. The ladybug, in turn, presses against the floor of the can, but neglecting gravity, the only force exerted on the ladybug is the force of the can on its feet. From our outside stationary frame of reference, we're the guy swinging the can around, we see there is no centrifugal force exerted on the ladybug, just as there was no centrifugal force exerted on the person who lurched against the car door. The centrifugal force effect is attributed not to any real force, but to inertia. Inertia is what's causing that pull on the string up. The tendency of the moving body to follow a straight line path. Try telling that to a ladybug. When you're in the G-force, is that what they call it? I always want to call it the gravitron.
G-force.
When you're in the G-force, do you feel a force?
Yeah.
Pushing you out?
Yeah.
It's not real. Just keep saying to yourself, it's not real, it's not real. It's not a real force. It's in fact inertia. It's inertia. You won't catch me on that ride. Not with that crazy little chain thing. Is that all I've got?
Or like the crazy guy then. Stop recording here.
Well, I used to have really big files. Now I'm good. Centrifugal force in a rotating reference frame. Now, what if we go on a field trip inside the can?
Why would we do that?
Well, because we're the magic school bus. Our view of nature is very much influenced by the frame of reference from which we view it. It all depends on your point of view, in other words. When we sit on the seat of a fast-moving train, we have no speed at all relative to the train, but an appreciable speed relative to the reference frame of the stationary ground outside. We have just seen that in a non-rotating reference frame, the force that holds an object in circular motion is a centrifugal force. For the ladybug, the bottom of the can exerts a force on its feet. No other force was acting on the ladybug. But nature seen from the reference frame of the rotating system is different. In other words, put yourself in the ladybug's shoes. In the rotating frame, in addition to the force of the can on the ladybug's feet, there is a centrifugal force that is exerted on the ladybug. Centrifugal force in the rotating reference frame is a force in its own right, as real as the pull of gravity. So the centrifugal force only really exists when you are inside the can, inside the rotating reference frame. There's a fundamental difference, though. Gravitational force is an interaction between one mass and another. The gravity we experience is our interaction with the Earth. People think that because the Earth spins, that's got to do with gravity. Because if there was no gravity, what would happen if the Earth spins? You go flying off the edge, because there's nothing holding you here except for gravity. I watched a movie last weekend called Mission to Mars. Gary Sinise, the guy from...
Is that where they like land on and there's green stuff?
They land on the face of Mars. The one guy goes out and a bunch of them are killed, and then he spends like a year up there by himself, right? And then they discover the big face, and they go inside the big face. Anybody ever seen that?
Sounds stupid.
Okay, so anyways, they got this space station, and it's rotating, and the guy is like going for a jog around, up the walls, and back around like this, because the whole thing's doing what?
So it's like
Rotate. It's like a hamster wheel, exactly. But because it's rotating, it's like there's gravity in there. When you're standing on the surface, there's like gravity. So it's a false gravity. If we were to live in space, we would need that to keep our body sort of, you know.
So the hamsters went fast enough and stop you go there.
Yeah.
Well, that's the classic, could you go all the way around in the swing thing, right? Yeah, have you ever tried that, Brandon?
Yeah.
Go all the way around? Every kid has tried that. You should try it sometime. I'm scared of swings.
I'm just get fed up and grab it and then swing it.
You can't go fast enough. I tried it.
But if you could,
It'd be cool. Yeah.
We did it with rockets.
They did, yeah. Okay. So, the gravity we experience is our interaction with the Earth, but centrifugal force in the rotating reference frame is not part of an interaction. It is like gravity, but with nothing pulling. Nothing produces it. It is a result of rotation. For this reason, physicists rank it as a fictitious force and not a real force like gravity, electromagnetism, and the nuclear forces. Nevertheless, to observers who are in a rotating system, centrifugal force seems to be and is interpreted to be a very real force. Just as from the surface of the Earth we find gravity ever present, so within a rotating system, centrifugal force is ever present. So once again, here's an example of nature where your point of view, your reference frame, is pretty darn important. All right, here's a couple questions for you. They will twist your brain. Do not, the answers are there, they're upside down, don't look at them. Zachary?
There's a video.
Got it?
All you gotta do is go to helium.
Okay, we'll get to it. Okay, we'll watch the helium balloon right away. A heavy iron ball is attached by a spring to a rotating platform, commonly known as a merry-go-round. Step and put the phone away. Two observers, one in the rotating frame, that would be the man, and one on the ground at rest, that's the woman, observe its motion. Which observer sees the ball being pulled outward, stretching the spring? Which one sees the spring pulling the ball in a circle?
I want to see the person on the outside.
Just stop and think about it for a second. I'll pause.
The lady who's the
Which observer sees the ball being pulled outward, stretching the spring? Which one sees the spring pulling the ball in a circle? I'll come to the answer right away. The spring in the sketch is observed to stretch 10 centimeters. In other words, this distance here is 10 centimeters right there, the distance that it stretches. Okay? When the ball is midway between the rotational axis and the outer edge of the circle platform. In other words, if you put the ball in the middle and then you run the merry-go-round, it's going to stretch 10 centimeters. If the spring support is moved so that the ball is directly over the edge, in other words, the guy picks up the post and somehow manages to attach it like right there. Now the ball sits on the edge. And then you spin it. Will the spring be stretched more than, less than, or the same 10 centimeters? More. Will it go farther out than 10 centimeters? It will obviously go off the edge.
I think
Will it stretch more? Will it stretch less? Or will it be the same?
stretch more.
It'll have twice the linear speed.
It will have twice the linear speed?
Yeah, at twice the distance.
Now, do I have the answers in non-upside down, or am I going to have to stand on my head? Easy for you to say. Okay, so it says, the observer in the reference frame of the rotating platform, that would be the man states that a centrifugal force pulls Rayleigh outward on the ball. He's in the rotating reference frame. He sees a centrifugal force pulling on the ball, which stretches the spring. The observer in the rest frame, the woman outside spinning it, states that a centripetal force supplied by the stretched spring pulls the ball into a circle along with the rotating platform. The rest frame observer can state in addition that the reaction to this centrifugal force is the ball pulling outward on the spring. The rotating observer, interestingly enough, can state no reaction counterpart to the centrifugal force. In other words, by sitting on the merry-go-round, he has just negated Newton's law. But there's no reaction force. He can't come up with a reason for the reaction force. All he sees is the ball pulling over on the spring. I don't know what's causing it. He doesn't realize he's rotating. Except his brain's going.
How does he not realize he's rotating?
Stone.
Do you realize the Earth is rotating right now, Zach? How do you know that? Is it really?
Yeah.
Like if we're lying?
No.
Do you see the model rotating right now?
Maybe the sun's rotating.
I don't know, man.
Maybe the Earth is the center of the universe.
We don't feel that moving, do we? We're born into it. It's just the way it is. No, you don't.
I do.
It's called getting.
Well, that's your superpower. You can feel the Earth moving. You can't fly, can't do anything else, but I can feel the Earth moving.
But that's true, I call it.
The ball will have, now when we move that support out farther sideways, the ball will have twice the linear speed at twice the distance from the rotational axis. It'll be moving fast. When you're on a merry-go-round and you want to go fast, where do you go? To the outside. If you want to go a little bit slower.
Oh, you gotta watch.
Wait. The merry-go-round of death.
Yeah.
There's more G-force on the other side.
You can, it's same distance, or sorry, different distance, same time.
So Miguel, see it. Watch the merry-go-round of death. Watch it.
Hang on, we gotta finish so we can watch the helium balloon.
The track is around the world triple.
Okay.
The track.
Yeah.
If you had it moving the exact same speed as the Earth in the opposite direction, what would happen?
What if the Earth, yeah, the Earth is one way, and the
Except
track is going the other way.
the track is moved, the Earth goes the next, so then it just so
You're going the other way.
yeah, exactly. So but you wouldn't feel like you're moving at all because it's going the same speed in the opposite direction.
Would you just meet up the other side like faster?
How would you do that?
When you go around the Earth?
What would the sun do?
You'd like stay on the same
I know I'd have to draw it out.
Would the sun not move though? The sun would be the exact same always.
Yeah.
Are you talking about the Earth rotating?
The Earth rotates one way and we go
Yeah.
the other way. So
Yeah.
it's
So
Would-
the sun
like,
would
it's
never
like you're
move.
staying and I go down the top.
The sun would
Earth
move.
would be moving. You could feel like you'd be moving fast.
Yeah.
Yeah, you'd be
I think
going
so, right?
twice the speed.
I don't know, I gotta think about that.
Feel like you-
Let me finish this, then I'll show you the helium balloon. Because the helium balloon is very cool. Okay, so, greater the speed, the greater will be the centripetal force, which will also be twice, and stretch the spring 20 centimeters. So it will, in fact, stretch farther.
So wait, if we run opposite to the Earth's rotation,